I'm not actually going to open this one up. I'm just going to talk about it briefly. But when we were working with the golf club demand example, we used historical data about this is the price we charged for the golf clubs, this is what demand was. This is the price we charged, this is what demand was. Okay, so we saw that and we plotted it on a scatter plot. We had a trend line, we put a trend line through it, and when the linear trend line, the linear trend line that we had through it, that developed an equation, that generated an equation for that, that equation was a simple regression equation. Okay, it's the same thing as a simple regression equation. And we're going to be working with a tool that does that, and then also can do it when we have more than one X explaining why. But right now we're just going to start out with that. So in that example, we did this for the purpose of getting those coefficients so that we would have slope and intercept. We'll talk about the linear one. So that we would have slope and intercept so that we could come up with demand and use that in a model that helped us set the right price to maximize our profit. That was our point in doing that. But when you look at historical data and you run regression on it, your typical purpose for that is using it for prediction. So you're going to look at, if I had this X, what would I expect Y to be? If I set this price, what would I expect the demand to be? Okay, that's what you're using that for. So we have kind of done this already, scatter plots, trend lines, predictions, all of that. The absolute percent error and mean absolute percent error, those are going to be the kinds of things in this software that will do that for us. We'll make those calculations for us. So we'll look at some of those in a few minutes. The example we're going to work with first is one where an individual was playing a video game multiple times, and we have data recorded for how many times, for each time they played the video game, what their score was. What we want to look at is whether the number of times that you play the game has any impact on or has some ability to help you predict what the score would be. One of the things you have to realize about regression, when we have this, what we call X and Y, independent, dependent variable, when we have those, regression doesn't tell you that one of them caused the other. It tells you how they're related to each other, and it tells you how much of Y can be explained by X. So we're about to get into a video game example where what's going to happen, and you'll see this, is that the more times the person plays the game, the better they get. You would assume that's what's happening, is they're getting better at it. Their score is getting higher. Okay. We're making that assumption, that is kind of causing that, but really that's not what regression proves. Regression just says that we can account for, explain some amount of the variation in the score based off of just the knowing how many times the person played it. And here's why. Because you could do a regression between a couple of variables like the sale of ice cream and the sale of, sod, grass, people buying it. Like, they might be positively correlated to each other. Does that mean that the more ice cream people buy, the more they want to buy sod and lay sod in their yard? Okay, no, highly unlikely. What does it mean? It's spring, the weather's getting warmer, and these two things absolutely correlate to each other because what's causing it is the weather, and at least with the ice cream, it's getting warmer, it's that time of year, you plant, putting your grass out, all those kinds of things. So we don't and can't say from regression, it's not a statistical test to say this caused this to happen. But what we will want to look at is how X explains Y, okay? How much of the variation Y we can see explained by X. All right, so we're going to answer a lot of questions about it, and I'm going to kind of walk you through it. Because half the battle is going to be getting all the stuff right in the stat tools, and then the other half is going to be the interpretation of the results that it gives you. So after we do the video game one, we're then going to do the one that comes straight out of the textbook, cost regression. We'll do for one product, and then we'll look at it for more than one product. Okay. And when we look at, just to mention, when we look at it for more than one product, we're actually looking at multiple regression. Okay, so what we refer to as multiple regression is when we have more multiple X's that are playing a part in helping us predict or explain Y. All right, so we'll do the second example of that. And then we finish up multiple regression next time and do some forecasting and all of that. But let's go ahead and look at our video game data. So here's the game data that we have. Number of times the game was played, that was the score on the first, the second, third. And this is collected all the way up to 60 times playing the game. And you would kind of see, I mean, I think you could look at it and see that the score was really getting better, you know, as time went by there, number of times playing the game. But that's what we're going to look at. I mean, that's part of what the whole point in us doing this. We're going to try to see what we can learn about this. All right, here's the thing. If you have, well, where'd it go? I was just in here using it, sorry. Stat tools, like, here we go. Shut down. Let me open it back up. All right, you got to open your stat tools, which mine was open a moment ago. I guess I think I closed all of Excel, and so I closed stat tools. But there you go. You have that stat tools tab on there. This is how you start. And again, I'm going to tell you, this is half the battle, just knowing all the little details and getting the right output. Because until you get the right output, you can't interpret it and answer your questions correctly. So you got to get the procedures of using a new software. Okay. So here's the thing. First thing you want to do in stat tools is define your data sets. Okay. Just move your cursor anywhere inside of this data set, which is our video game data. Okay, move your cursor anywhere inside of there and go to the data set manager. It will automatically pick up on your whole range. It will recognize your whole range and it'll say, do you want to add that range as a new stat tools data set? And you'll say yes. And then you will give it a descriptive name. So because as time goes by in a particular worksheet, you may have more than one range defined. And so you want them to be names that would make sense to you when you go back and look at them. So I do, okay, let me show you what I'm going to name it. I'm going to name it video game regression. And there's a reason I'm naming it regression instead of just video game. And that's because, not immediately, but in just a short while, we're going to be also setting up a prediction range, and it will be different from the original data range. And so for me, it's a lot easier if I put those names into the names I name it. Okay, like I'm going to call this one video game regression, and in a little while I'm going to have one I'm going to name it video game prediction. That tells me which set is which when I'm working with them. Okay, that just helps me. You can use whatever naming convention you want to use. But all I did was give this the name video game regression. When I click OK, that has been defined as a data set that stat tools can now use. Okay. Yeah.
Did you go to data utilities for that?
Data set manager. Data set manager. And the first thing it'll say when you're inside of a range is, do you want to make this a new range? So that is defined. And really, one of the things that you want to do would not be unusual, that what you might just want to do is plot the X and the Y against each other, just to see if there's even a relationship between these two things that's worth pursuing, that's worth running a regression over. So it's not uncommon just for a first step to be plot these things and look at them and see what you kind of learn about them. Okay, so I would go to this little drop down where it says summary graphs, and the summary graph that I'm going to use is a scatter plot. Now, I'm using the stat tools to do this. Could I have just used Excel to make a scatter plot? Absolutely. But I'm in the middle of using stat tools, so I might as well use theirs. Okay. So I'm going to use this one. I'm going to do a scatter plot. And here are the things that you have to watch. One, did it pick the right chart type? Well, if you pick the right chart type, a scatter plot, it's going to say a simple XY chart, and so you will be good there. But just in case you clicked on the wrong thing, you want to check that. The next thing, and this will come up in almost everything we do, it'll say which data set. All right, well, you know right now, we just started this, we only have one data set. Later, we will have multiple data sets to choose from, but right now we just have one. So, yes, the video game regression data set is the one that I want to use. Okay? And then it shows me the two variables. It shows me the number of times it was played and the game score. And it's going to ask me which one is X and which one is Y. Okay, well, which one of those is X? The number of times played, and then Y is the game score. That's the assumption we make about the one that we think impacts the other. Yes, I know that in the end, in regression, you don't say that one caused the other, but you do set them up in the way that the one that you would think would be the independent and the one that you think would depend on that. Okay? So that's my X and Y. Okay, here is the other thing that you need to do. Okay, you had to make sure it was the right data set. You have to make sure that click the right X and Y, and you'll have to do this. And I realize this test is a couple weeks away, but wherever you are, you're going to want to click on this button that does your settings right here, because you want to look at where it's going to place this item that you're requesting, a scatter plot, regression analysis, whatever it is you're placing on, or I should say generating, where is it going to place it? And you have a lot of choices of places that it can go. And the one that we're going to work with, as we work through them, and that we would want you to do when you get there the day you're taking the third test, would be to put it after the last used column in the active sheet. We don't want it generating a new workbook. That would be bad. It costs, now we'd have stuff in two different places. You can't do that. We're not going to want you to make a lot of new sheets. It's just easier if you put it after the last used column in the active sheet. And then you click OK. It's going to ask you if you want to save those settings, and you say yes. Now, once you've done that on your own machine, I think you're fine and you won't have to do it again, but you can check it as you open up new workbooks. Again, though, at CASA, you're going to have to make sure that that is set that way. That's 2 weeks from now. All right, so I'm clicking OK to generate this scatter plot. And there it is. And the scatter plot plotted the number of times of playing the game against the score that we got. And you can see there's a nice, would appear to be a pretty decent relationship between those two. You can kind of see that just looking at the plot. But the other thing is, as a part of that, it automatically put in there the correlation. And so the correlation is telling you that there's a decent relationship between these two, because it's 0.855. Okay, let me tell you what the correlation is. If you took the actual Y's that occur, in this case it would be the actual scores, and you plotted them against the predicted, and these are also sometimes called the fitted scores, this is what would happen. All right, what do I mean by actual? Maybe we should talk about what the predicted scores that go with this are. Remember when we were doing the golf club example, we would have a line drawn through here that we would consider the best fit line, okay? And why is it the best fit? Because it took the distance between what really happened and the point that point on the line, and it minimized those differences. We call them residuals. Minimize those. In fact, the line was built in order to come up with what we call the least squares. Here's what the points on the line are. When the line is drawn through here that best fits this, if we said, okay, we've played the game 40 times, we would go up to the line, and whatever that is, Y, that's our predicted score. Okay. So the regression tool, the trend line, those things, they go in and they look at the distance of every single one of these between what really happened and what would have been predicted, which would have been the point on the line. And that residual, okay, that error is squared, and that line is perfectly drawn through there to be what we call the least squares line, because the least squares line minimizes that error as much as possible. That line, in this case, has this 0.855 slope. What that means is, and I'm show you just on something that it isn't really going to happen often, but if your actual score was 1 and your predicted would have been that it was 1, well, okay, you're good right here. I think you can plot that. If your actual score was 2 and you predicted it would be 2, if your actual score was 3 and you predicted it would be 3, if its actual was 4 and you predicted it would be 4, okay, I'm getting kind of off on my little hashtag of the mark here. Okay, 3, 3, 4, 4, okay. In other words, your line over there would have been going through every point because they would have been perfectly predicting. Your actuals would have been exactly what you predicted. And so when you plot your actuals against your predicteds, lines where they were. When you plot them, you would have an exact line that has a slope of 1. And that slope would mean that your correlation is equal to 1. And what you want is a correlation that's as close as possible to 1. Unless this is negative related and you want to slip it close as possible to -1. But you want it to be, the absolute value of it to be as close as possible. Well, it's 0.855. It's not bad. Okay, it's not bad. So we certainly look at that and see that there does appear to be some relationship between those two variables, between the number of times you played the game and the score that you get. So we're going to go forward with regression analysis now. So we're going to click on the regression classification little drop down and choose regression. And this box will open up. When it says at the top, regression type, and it says multiple, and you're thinking to yourself, no, we're not doing multiple regression right now, we're doing simple regression, there isn't a simple regression choice, and here's the reason why. Simple regression is multiple regression, just only with one X. Okay, so it's a category of being multiple regression, it just has one X as opposed to multiple X's. So they don't differentiate between the two of them in this tool. They just call them all multiple. So every time, we're never going to use stepwise forward, backward block. Every time you come into this, it should say multiple. It probably will, but it should say multiple every time you come into this box. Then the next thing is, what's your data set? Again, that will not, if you have multiple data sets in your workbook, that will not always come up with the one you meant for it to come up with. So you just have to double check that to make sure you're doing the right one. We've only defined one data set. It's the simple, what we call the video game regression. Okay, video game regression, I defined it, that's the only one. So I'm okay, but once we get into ones where we have more than one, it may come up with the wrong one showing, and you need to pick the right one. All right, and then it's got, instead of X and Y, it's referring to them now, because we're doing regression, it's referring to them now as the independent variable and the dependent variable. So which one of these is the independent variable? The number of times playing. And the dependent variable is the game score. So that's what we refer to them as in regression as opposed to the X and the Y. So, check that. You made sure that data set is right. Put those. You won't be messing with anything here where it says parameters. For graphs, if you were going to do a couple of them, a couple of good ones would probably be the fitted values against the actuals, which is that chart that I'm showing you over there, which is going to have a 0.85 slope as opposed to a slope of 1, but that's still pretty good. The residuals versus the fitteds, we'll talk about that briefly. And right now, I'm not going to include a prediction set. I want us to do everything slowly in pieces and look at one thing at a time. Okay. So, check through all these things, get on the right data set, click the right independent, dependent variables. I might want to see these two charts, and I click OK. And this will generate for me my regression output. And I didn't check, I didn't real quick say, look to see where it was going to place it, because I'm in the same workbook where I already saved those settings saying put it on the same worksheet. So I wasn't anticipating that it was going to go anywhere different, but you can always check that if you want to be sure. So here's what it generated. What does that look like to you? Multiple R. It's what? It was the, yeah, it was the correlation. That was the same as the correlation number that was under the chart. Okay. So that is telling us the correlation between those two variables. It's actually quite good. This one, let's write some of this up here. So when you look at the output, you see multiple R. That's the correlation, which was already listed under the chart. Okay. R squared.
Is that like the other R square we use?
Yeah. R squared the way that you know what R squared is it is the percent of the variation in Y that can be explained by X. So for us, that's the percent of the variation in the score that can be explained by how many times you play it. So for us, how much of the variation in the score can be explained by the times you play it?
73%.
73%, which is good. It's good. And R squared is multiple R squared. Okay, that 0.855, that's squared. That is, I mean, that is what it is. This squared is R squared. Okay, and but its definition is the percent of the variation in Y that can be explained by X. This standard error of estimate works like and is very much like what you think of as standard deviation. Okay, how many of you had statistics already? Okay, so any of you not have statistics yet? Okay, in the future this isn't going to happen because, you know, they switched that around, but you guys fell under the catalog where you didn't have to have it before you had this other stuff. But, so you may not have seen this, whereas the people who've had statistics have seen this. You may not remember it, but you've seen it, okay? So, just real quick here. The standard deviation of a number is how dispersed those data values are. If you took data values and you plotted them kind of histogram-like and imposed a curve on it, if that's a real tight curve, then the standard deviation is very small. It's a measure of dispersion. The data is not dispersed very much. If that curve is very broad, then the data is very dispersed. Okay. And what standard deviation tells you is within how many standard deviations from the mean do you account for certain percents of your data. Okay. Within one standard deviation of either side of your mean, you account for 2/3 of your data. Within 2 standard deviations either side of your mean, you have accounted for 95% of your data. And that's a lot. Okay. If you go out 3 standard deviations, we think you've pretty much accounted for all of it, but you can never say 100% on anything that, you know, can vary. So it's like 99.7% of your data is 3 standard deviations. What you see in statistics, and you'll remember this, is we use that 95% confidence interval a lot, okay? Because you've gone 2 standard deviations either side of your mean, and it is accounting for about 95% of your data, okay? So here's the thing. A data set where the curve is very tight is going to have a very small standard deviation. And one where it's very spread out is going to have a very large standard deviation. And that part, you know, it's just depends on what your data is like, but that is what standard deviation is telling you. This standard error of the estimate is almost that same thing. It works like that and is pretty much just about that value. And we're going to see that in a minute when we do some predictions. So we would assume that whenever we get a predicted amount, that it would, for the most part, be within 2 standard deviations either side of that amount would be reasonable. Okay, so we need to know those. We're not going to work with the ANOVA table stuff. here's something else that we're going to need to pay attention to. And it isn't going to be as big a deal when we're working with simple regression because you've only got one x being related to one y. And if you had decent multiple r's and r squared, then these are going to be fine. But we will pay more attention to this on multiple regression with several x's because we want to make sure that every variable that we put in here to try to explain y is significant. And the way we know if it's significant or not is if that number is less than 0.05, then it's significant. If that number is 0.05 or greater than 0.05, then that would not be significantly contributing to helping us explain y. Okay? This one, yeah. This is perfectly fine. It is helping explain y. Okay? The number of times we played is very significant in helping us explain y. So that's important. Then we want to know what those two numbers tell us. And those two numbers, those are the coefficients. Those are the coefficients of our function. Okay, those are the coefficients where, and I'm going to put words into this, that's our constant, that's our slope and our intercept. Our constant's our intercept. Our coefficient that goes with the number of times playing, that's our slope. So we could take those numbers and write our own equation. And this is what it would look like using our variables, not x and y. Your score would be equal to, what's the constant or the intercept? 11,735.8 plus times the number of times you played. Using words instead of x and y. Okay, that's x, that's y, but we know what this looks like. Constant plus the slope times the intercept plus the slope times the x. All right. We've seen this a lot because we started seeing it a lot when we were doing the demand. And so we've seen that equation a lot of times, and plus you just know that equation. You know, the slope of the linear line equation. What do those numbers actually mean, though? What do you think that means, that 1119? What is that telling me?
It's a positive slope this many times.
Okay, so it's a positive slope. So then in terms of our variables, what does that mean?
The more times you play, the better score you're going to get on average.
Right. And in particular, one more time of playing the game should do what?
Give you 1,000 extra points.
Give you about this, yeah, that 1,119, extra points. We would predict that that would be true, that we would get about 1,119 points additional for every time you play the game. What does that number mean right there?
Maybe up before, add to it?
What was that?
Yeah, I don't know.
It's like one of your lowest scores, right?
It
You play
is,
it one
because
time,
it would be what?
the first time you play.
Yeah, just put a 0 in here. That's your score, isn't it? Okay. Now, 0 sounds a little weird because you can't play it 0 times, but our practical interpretation of this would be that you basically start about here.
Starting point.
Yeah, it's kind of a starting score, like first time you played it would be about here. Or maybe the first time you played it would be this plus this, but that's close enough to what we're trying to get at. And does that make sense?
And that'll stay the same, like for...
Regardless, we just explain it in terms of what our x and our y are, but yeah, that's what it means. For every one increment increase in this is what we expect y to increase. Okay? And this is the value of y when x is 0. So I went back to generic way of saying it with x and y and not with score and times played, but yeah. All right, so you need to have gotten to the point where you have regression output or you can't answer any questions on a test. So obviously we're going to go back through the stat tools stuff and talk about it again on everything that you do. Okay. But when you get this output, you should be able to explain the things I have highlighted there, or interpret or use the things I have highlighted there. Okay, you should recognize that multiple R is the correlation between those variables. And I probably wouldn't ask it like this, but the way we get that correlation is that's the slope of the line when we plot the actuals against the fitted or predicted values. You should be able to tell me what R squared is. You should be able to say 73% of the variation of your game score can be explained by the number of times you play. You should look at the p-values and know that those are significant and they're working in your model correctly. You know, they're helping out, that times played is helping you predict or explain the score. And then you should be able to take those coefficients, write out the equation using words, not an x and a y, but words, and then interpret those coefficients in relation to what we're working with. Like, you know, for every additional time you play, you expect that your score would increase by 1119. You know, from the very beginning, kind of a reasonable start score is probably around 11,700. Okay. The other thing that was plotted here is that plot. You know, I did a perfect one where actual and fitted were, you know, we predicted this, we predicted that, you know, and everything was exact and we had a perfect one. Well, this is the plot of the fitted, or the actual, predicted versus what actually happened with the game score. And this, the line that go through this has a slope of 0.855. Okay, so that's the correlation line. And this plot, the other plot that I had that I checked in the box to have it generate, was one where it plots the residuals. And the residual means the distance between what was predicted and what actually happened at each x, okay, against the predicted. We're not going into a lot of stat theory on this, but you actually want this plot to look like this, with no pattern whatsoever to it. And it's one of those things that statisticians look at to see whether assumptions of your model have been violated and whether this is actually, you know, a good model to use or not a good model to use. And if you see patterns in that, that can actually indicate some problems. And so we don't want to see patterns in this. But we're not going to go into all the stat theory on that. We just don't want to see patterns in that. And that's the data that it generated to plot that. Okay, so we are going to need to do this, but another thing that we will need to do, and I would normally do this all at once, but I wanted to do it in pieces for class so that we were learning one thing at a time. I'm going to go in here and insert some new columns because we want to do some prediction. We want to use stat tools to do some predictions for us. Here's the easiest way, if it isn't already set up for you, here is the easiest way to set up a prediction set. Copy the column headings, which are like your variable names, right? So copy those